Hi, welcome back. This is ACM ICPC Training 41. Wow, it's 41. It's just like I am 41. Okay. This one is section 2.3.2. Cow pedigrees. Cow pedigrees. It's just family tree stuff. Let's take a look with a question. Pretty clever question. All right. Cow Pedigrees by, well, I can't pronounce this name. 2003. Anyway, Farmer John, well, John has a lot of job to do. Farmer John is considering purchasing a new herd of cows. In this new herd, each mother cow gives birth to two children. The relationships among the cows can easily be represented by one or more binary tree with a total n nodes. The tree have these properties. The degree of each node is 0 or 2. So either you have kid or no. Either you have kids. If you have kid, you have two kids, or you don't have anyone. The degree is count from the node's immediate children. That means just look as I said. If you have children, you have two. All right. Otherwise, you have none. The height of K. The height is the number of nodes on the longest path from root to any leaf. A leaf is a node with children. That means the guy has no children. How many different possible pedigree structure family tree are there? A pedigree is different if its tree structure differs from that of another pedigree out to the remainder when the total number of different possible pedigree is divided by 9,901. It's a prime number, I think. Okay, you are given and how many cows, actually how many nodes. Actually, if we just talk about trees here, we don't talk about cows anymore. Tree, you are given two numbers. One is how many nodes in this binary tree, and two, the K, what's the length, or what's the depth, what's the height of this tree. You are given 5 nodes, and this tree's height is 3. All right, pretty much cool. And then you want to find out how many structure I can make, how many trees I can make. Here's an example. Here's the solution actually. All right, 5. You see this one and this one. Actually, there is no difference between the representation. I mean, if you don't consider their labels, but this does consider as 2 different trees. All right, but how can we actually make it happen? How can we really know how many possible way to construct such trees with so many we have so many choice, we have a lot of height. Okay, let's consider if I want to, if we don't consider this guy first. All right, and now I have a lot of subtrees, a lot of solution came out, every combination of 4 nodes. No, not 4 nodes. Actually, you can have 1 node, 2 nodes, 3 nodes. Actually, it's what I need to break this first. You see, because everybody is having 2 children, along with himself is 3, and he is either a root or he is a children from someone else. So actually, the total node of this tree has to be odd number. Never gonna be even number. Only gonna be odd number. All right, this is the thing. So let's just, seems like we don't consider this first. We have a lot of combination of only one node. One node does consider as a tree, and 3 node as a subtree, like here, or like here, or here, or here. And when we want to add this one, we need to consider who I might connect to. All right, because I am higher level, so I definitely have two children. So my children is 2 subtrees, and this 2 subtree is a combination of all the possible combination of these 2. And there's a constraint. The constraint is we 3 together may the root, my left and my right, the sum of the node has to be equals to n, and our height has to be k. So how is that happen? So you see, so after I add this root, I am actually having my subtrees, maybe 2 subtrees. I can have as much as 2, and in fact, at least one of the subtree has to be 2, has to be k minus 1. All right, so either the left one is 2 or right one is 2, or they both as 2, if they actually make sense. For example, this way, if I have here 2, doesn't make sense because I have 2 more nodes, I have 7 nodes. All right, and then we consider a much more stranger case. If we are not considering these 2, we're just considering how to construct this subtree, we can see a pattern here. If we want to consider this one, we actually need to consider, all right, my left and my right and me, we 3 have to be 3. The number of nodes have to be 3. And my substructure, my subtrees, my left or my right can at least can have a height as much as 2. Am I right? Yes. Okay, this is how the thing work. How can I search? How can I search out this stuff in the dynamic programming way? Okay, let's take a look with the code. Alrighty. Okay, here are some heads up. First of all, your height is never gonna exceed 150, and your nodes is never gonna hit 250. 200 actually. I just add 100 on. This is actually the height as long as go as 100. And ST means the subtrees is also the same thing. Okay, we read NK. Okay, F1. What means Fij? Fij means if I have a height I and number of node j, I have how many ways to construct the tree. Okay, so you have only one and I have only one node, so I have only one way. This is the foundation base. So from the height 2 to the k, we need to search out, and then from number of nodes, from node 1 to n, and we know because we only going to search through like odd number, so we just simply plus equal 2 here. We don't plus for saving time, for saving some errors. And this one is if, let's say, okay, if one of my substructure is k, either left or right, have a number of node as k, the small k, then that means this k has to constrain by this case, because total number minus 1 minus k is the largest it can go. It's the largest it can go, because we need to save some space for the left or for the right. All right. And if it's not equal to that, then the factor equals to 2. Why equals to 2? Because we have 2 children. Otherwise, we have 1. Because we are only going to search like one identical. Actually, for example, like the case we have seen, we have only considered the first one, but the second one actually the mirror case of the second one. So we just, if we have a factor, we just times 2 about the combinations, and that's it. Fij from the height 1, and if I have j node and a factor, and then I start to calculate how many combinations, right? Then we have this subtree thing. Subtree ik, maybe I should use like n and m, means for I have a substructure telling me how many combination I can find from height n with node m. So that means if my left, why I minus 2? Because I minus 1 is the well, is awkward. We need to search through all the combination along with I minus 1, because I minus 1 is only one case, but we have so many substructures inside, so we need to search through all the I minus 2k. Actually, you see, ST is not exactly as F, because F is only going to introduce you only one solution, but I minus 2k is actually representing fi minus 2k plus, no, fi minus 2k plus fi minus 3k plus I minus 4k, blah 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 blah. We ST recording all the combination equal or below I minus 2 height. All right, and this is the whole combination of your left times fi minus y j minus 1 minus k, your right. That means your left is that means your right is have the height of I minus 1, and your left is less than that. It's less than that, but just as equal. Same goes if my left has the height of I minus 1 and my right doesn't have that, so I need to sum up all those combinations, and finally we have a equal. So if my left have a k, right have a j minus 1 minus k, we combine each other, we have a n. We have a j, and then we just modulus it by 9,901, and then we need to configure what is ST. Here we have a solution. Okay, ST is ST I minus 1. That means not considering a root. I minus 1 height k is equals to what? Equals to fi minus 1k plus sti minus 2k. That means I have I minus 1k, these combinations, plus everything you have from I minus 2. So I can build up sti minus 1k. All right, it's a little bit complex here. You need to fill it, and then of course this solution is also be modulus by 919 9901. And finally, it always like that. Dynamic programming always like that. You just need to find when the height k and your node n and how many ways to construct a tree, and this is the solution. This question is a bit tricky, actually. It's kind of tricky, but we need to know is there is a special structure there. Dynamic programming is always like this. He has someone to take note with the pass, either only the pass from just one step back, or the pass from the whole long, but it's actually the thing is same. It's dynamic programming. The thing is same. Well, you actually got to spend some time to feel about that code or about this method. If you have any question, I would like to answer it. But it's not very easy to hold up like this. All right. I will see you next time. Bye-bye.